Alright, welcome back. In this video, we're going to talk about the solutions and grading for the problems in set 3. So here is the first problem, and part A asks what is the 70th percentile of the distribution of stopping distances. There are multiple ways of solving this problem, and it's important to know, first of all, what kind of distribution you're using. And in the problem, it says the stopping distances are approximately normally distributed, so that allows you to use the normal distribution. And over here, we see one way of solving this. So for part A, what the official solution states, it defines the variable, what x stands for, and it specifies that x is normally distributed, and it says what the mean and standard deviation are of that variable, and that information is from the original problem. What they do is they calculate the z-score, and the z-score corresponding to a cumulative probability of 70% is z equals 0.52, and therefore, using the z-score, they can find the percentile value by using the z-score formula, but solved for x. So that's using the same z equals x minus the mean over the standard deviation, but solved for x. You've got all three of those values, and you get 128.4. That's one way of doing it. In fact, I would suggest that the solution for part A here is incomplete because they don't say in any way how they got the z-score to be 0.52. But we can see down here in the scoring section, part A is scored as follows. It's essentially correct if you indicate which distribution is being used, so you would have to say it's normal, along with what the parameters are. The mean of x is 125 feet, the standard deviation of x is 6.5 feet. And you have to correctly calculate the percentile value with appropriate justification. So, here are all the different ways that you could get distribution parameters and calculation of distance. You need all three of those to get an E. If you write normal 125 6.5, you're good for distribution and parameters. So then all you'd have to do is state that the stopping distances have this distribution and calculate from there. You could use the z-score formula. That implies that it's a normal distribution and the parameters are in the z-score formula. So that would work as well. If you write the calculator speak, so the other way of calculating the 70th percentile here is to use inverse norm and calculate the score such that 70% of the area is to the left. So if you just write that and you give the answer, you need to provide a sketch of the curve. You need to show the curve if you're going to use the calculator. And that is the case for anything you use the calculator for. If you're using like normal CDF or binom CDF or PDF, or if you're using inverse norm or inverse T, always show a curve if you're going to do that. And your curve must include correct labels for center and spread. I would go ahead and put 125 in the middle, and then actually count out 6.5 feet on each side for 3 standard deviations. So correctly label that as well. Also, if you use inverse norm with the parameters included, so it's different than this one. This is strictly what you put in the calculator. Here you're saying what the mean and standard deviation are equal to. Then you don't even need the curve because you're showing that it's normal and what the mean and standard deviation are. So if you're going to write the calculator speak, I would put in at least what those numbers represent. That's a safe thing to do. But if you're going to use that calculator speak, I would also recommend drawing the curve. It's partially correct if you only do 2 out of those 3 things. So if you were to put in inverse norm here and you put the correct answer, you're going to get a P, even though that's correct. You need to either put the mean and standard deviation parameter symbols in there, or you need to provide your curve sketch. And it's incorrect if you only do one of these 3 things. Okay, so hopefully one of the goals of these videos is to show you what you need to put and what you don't need to put. So for part A, if you calculate the z-score like they did up here, that's fine. But if you're going to use inverse norm, you know exactly what you need to put in and what you can leave out. All right, so for part B here, what is the probability that at least 2 cars out of 5 will stop at a distance greater than what you said in part A? Okay, so we were using the normal distribution for part A, but for part B, when you see at least 2 cars out of 5, I'm immediately thinking that's a binomial question. And in fact, it is. So for part B here, they said that in part A, we calculated that this is the distance that has a probability of 0.7. So getting the probability of getting a distance greater than this is 0.3. So again, they define the variable. This time, y is the number of cars out of 5 that can stop greater than 128.4 feet. And y is binomial, and they specify n and p, which are the parameters for a binomial variable. Okay, so instead of mean and standard deviation, for binomial, it's going to be n and p. And so they put the probability that that is at least 2, greater than or equal to 2. You would have to do the complement rule. So that's 1 minus the probability that it's less than or equal to 1. And they write the binomial formula here to get 0.4718. So again, let's look at how this is graded and how what you put down could influence what you need and what you don't, because you probably wouldn't write it this way. This was back from 2009, so some things are a little different now than they were then, and I'll let you know what those are. You would not be expected to write this. Okay, so for part B, it's essentially correct if you say that it's binomial and you set up the probability correctly by finding p and using p to find the correct binomial probability. So again, you need to include information on what distribution you're using, what the parameters are, and how to calculate it. So they talk about if you use binom CDF, and that is what you write down, which that's how you're going to do this problem, almost certainly. This is what you would do. So if you use that and you give the answer, you need to describe the distribution of the variable itself. This is not telling you anything other than what you put in the calculator. You can know to use this without having any clue what those things represent. It is possible. So what the graders want to know is that you know what those things stand for. So you would have to say that the variable has a binomial distribution. You could write that as a b or bin. If you write it this way, this isn't what you put in the calculator. This is how you represent a binomial random variable. Binomial with n and p. If you write this binom CDF stuff down and give the right answer, you have to describe somehow what the variables are. And they do that here by saying n equals 5 and p equals 0.30. So you could just write that out in a sentence, or you could do it this way. Okay, it's partially correct if you only do 2 out of those 3 things. If you write the distribution parameters, you don't need to set up the binomial formula. But if you do write the formula, like in the solution above, you're good. Okay, and if you just provide 1 minus binom CDF with what you put in and the answer, again, that will give you a P even if it's the right answer. So what they're saying, the difference between just typing this or writing this down and getting an E is writing this information. You could either write it one of these 2 ways, or you could write out, hey, this is a binomial random variable with n equals 5 and p equals 0.3. That tells them you know exactly what distribution you're using, which is important. Okay, part C. What is the probability that a randomly selected sample of 5 cars will have a mean stopping distance of at least 130 feet? Okay. So we use normal for part A, binomial for part B. They're now asking about something involving a sample of 5 cars. So we're using now a sampling distribution model here, because they want to know something about 5 cars, a sample of 5 cars, not just one. So for part C here, we're talking about X bar, okay? The sampling distribution of the mean. Okay. Because the stopping distance for each has a normal distribution, then you can say the distribution of the sample mean is also normal. If they had not said this in the original problem, you would have to check that using conditions. But since they gave you that already, you can go ahead and say the sampling distribution is normal. With a mean of 125, and remember, when you're talking about a sample of cars, if that's what you want to talk about, the standard deviation, you have to divide by the square root of n. So the standard deviation for a single car is 6.5. But the standard deviation for stopping distance of a sample of 5 cars is going to be smaller than that. Divide by the square root of 5, that's 2.91. So what they did here was just calculate the z-score by taking 130, which is the number from the problem here, subtracting the mean, 125, and dividing by the standard error here, 6.5. That should be divided by the square root of 5. That's going to be the 2.91 down here. Okay, and from there they can get the answer. So in terms of scoring, it's essentially correct if you provide all 3 pieces again. You need to describe the sampling distribution and its parameters and calculate the answer correctly. So if you use the z-score formula but do not state that the sampling distribution is normal, that only counts for parameters. That doesn't count for sampling distribution. If you provide the normal CDF information, you need to sketch the curve to get an E. And your sketch has to include labels for center and spread, so put the 125 in the middle and go out by 2.91 for each of your standard deviations on the sides. But again, if you put in normal CDF, but with the mean and standard deviation notation in there, the mean is 125 and the standard deviation is 2.91. All you need is that in the answer. So what I've been saying in class about how the boomers don't want to see the calculator speak. They just want you to show them that you know what those numbers mean. The 125 is the mean for the population. The 2.91 is the standard deviation for the population. Okay, and let me pull up normal CDF here. Okay, my calculator is super old, so it doesn't have the window. It's possible, I don't have a newer calculator on me at the moment, that you're typing this stuff in. You're looking at it on your calculator. So when you're writing it on the paper, if you choose to write this, go ahead, when you type the numbers into the calculator, write out what they represent. And that will be more likely to give you a higher score. That will give you that E. It's partially correct if you only get 2 out of these 3. So for example, if you just put normal CDF like this without the mean or standard deviation notation, even if the answer is right, that gives you a P. And you get an I if you get at most one of the components correct. Okay. If you give the right answer, but that's literally all you put, that's going to be an I. If you use the T distribution instead for this part, that is an I. The sampling distribution here can be assumed to be normal because the individual tires were normal or came from a normal curve. And you should, if you get penalized for using the calculator syntax, at least back in the day, in 2009, you would only be dinged once for that. But there's no reason to get dinged at all. So if you're going to write that calculator speak, at the very least, don't write it like this. write it like this, with the parameters included in there. Okay. Let's talk about question 2. Question 2. Okay. Let's get in here. All right. So they give us a lot of information here. Do you think television commercials are effective to promote a new product? Okay. So December 2008, they gave this survey, and they gave it in December 2007 as well. And we want to know if the data provide convincing evidence that the proportion has changed from 2007 to 2008. Cool. So here we go. We're going to go through our solution here. So this is really funky type here. It's not great. This is from 2009 also. They define their variables first off. Okay, and I probably could have done a better job telling you all in the hypothesis test that we did in class to define your variables. So they're going to let P07, and the 07 would be a subscript. Okay, that represents the proportion of adults in the United States who have answered yes in 2007, and then they've got 2008 as well. That means the same thing for 2008. So these are the hypotheses they're testing. They've got the null hypothesis here, P07 equals P08, versus the alternative hypothesis that they are not equal. Okay, first step to the hypothesis test, write your hypotheses. And the reason that is a not equal to sign is because it asked whether the proportion changed. Not increased or decreased, just changed. Now, I do want to talk about this for a second. This is not how I would have taught you to write that. I probably would have told you to do this instead. P07, or wait, this is going to be, yeah, you can do P07 minus P08. Okay, so I would have had you write the null hypothesis this way, because this shows that you're taking the difference of two independent proportions. So that would mean that your alternative hypothesis would be, it's going to be tough for me to write a not equal to sign, so I'll just put NE for not equal to. Okay, so these hypotheses that are in the solution and the ones here, whoops, this is the alternative hypothesis, these are the same. Okay. So I don't want you to think that you have to write it this way. You can write it the way you've been doing it. All right. So we've got our hypotheses here. So that's step 1. And the reason that they mention steps is because that's how it's scored. So there are 4 steps to this problem, and you can get an E, a P, or an I on all of them. And just writing the hypotheses and stating the parameters is the entire step. So for that step, it's essentially correct if you identify the correct parameters. Okay, the correct parameters. So that's these proportions. So just state what they are, what they represent, and both hypotheses are labeled and state the correct relationship between the parameters. And you can do it the way that they did it, or writing them this way. It's a partially correct if you do one of those two things, but not both. So if you wrote these hypotheses, but didn't state what these things meant, what they represented, they would actually give you a P for that. So if you're going to use notation similar to this, which I would recommend, you have to define what those variables represent. And it's an I if you don't do either one. It says either defining the parameter symbols in context or simply using common parameter notation is sufficient. Okay. Oh, so if you write it this way, then that's enough. You don't have to define them. Okay, there you go. So just putting like P1 minus P2, that would not work. If you're going to do that, you have to put subscripts on there that would represent the variables. If you're going to do P1 minus P2, you have to say what P1 and P2 mean. Okay, step 2. Identify the test procedure by name or formula and check conditions. So this is going to be a 2-sample z-test. That's all you'd have to write there. You don't have to say you're comparing proportions. It's a 2-sample z-test. And you would then go through your conditions. Okay, first condition is that they're gathered from independent random samples from the 2 populations. And it's met because we're saying from the problem they were randomly selected in 2 different years. So that's your randomization condition that's checked. Although we're not told whether the samples were selected independently, this is reasonable. Okay, so in terms of independence, independence was an assumption that you needed to check in 2009. Nowadays, we use the 10% condition for that, so don't worry about checking independence by itself. You got randomization. You would have to check that the sample sizes are large enough. So that's your n times p and n times q being at least 10. That's what they're checking here. And they say this additional condition may be checked. This is the 10% condition. This is now a condition you need to check. Okay, so you've got randomization, large enough sample, which is n times p and n times q being at least 10. It says or at least 5, make it 10. And the 10%. Okay, so that's step 2. You get an E if you did all 3 things. You have to identify the test that you're doing. You can either say 2-sample z-test, or you can use the formula, like the z-score formula. Okay, and then check your conditions. Partially correct if you do two of the 3, incorrect if you have 1 or none. Step 3 is to actually calculate the test statistic and the p-value. So here we've got the calculations of both sample proportions and the combined proportion here. Remember, you need that for a 2-sample z-test for proportions. And so your test statistic has this formula here, where that p hat c is this one here. So they show the steps for calculating that out, and they get negative 2.82 for z. And then they calculate the p-value as 0.0048. Of course, when you do this test, you would have a sketch of the normal curve, and you would have both sides shaded, both ends. That's why they do 2 times the probability of this, because they need both the left end and the right end. Okay, so step 3, showing all this work for calculating the z-score and the p-value. Essentially correct if you do that correctly. Partially correct if you calculate the test statistic but not the p-value. I think, like, if you got the right z-score but then didn't multiply the probability by 2 or something like that. Or if you calculate the test statistic incorrectly, you make a mistake with the formula or something, but then you calculate the p-value correctly. Okay, so you can screw up from the z-score to the p-value, or you can screw up with the z-score but get the correct p-value for that z-score, still get a p. Okay, so if you think you mess up somewhere in here, if you don't remember exactly what the formula is for the z-score here, write something. Calculate a z-score, and then calculate the p-value from that. You can still salvage a p from that. Okay. And then step 4 is taking that p-value, stating your decision, what you're doing with the null hypothesis, rejecting or failing to reject, and then what does that mean, your conclusion. So, because this p-value, 0.0048, is smaller than, you would just say alpha equals 0.05 because it's not given. Okay, they say any common significance level. You don't have to go into that much detail. Just say it's smaller than this. We reject the null hypothesis. Okay, that's important. You need to write that. What does it mean to reject the null hypothesis? That you've got convincing evidence that blah, 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 that's the context. That's essentially what this is saying. Whatever your alternative hypothesis is. Okay. So for step 4, grading-wise, it's essentially correct if you give the correct decision reject the null hypothesis, and provide justification, okay, based on linkage between the p-value and the conclusion. So as long as you stick to the template that we've used, you should be good there. Remember to put it in the context of the problem. Partially correct, if your decision is correct, you reject the null hypothesis, and you link it to the p-value, but you don't put any context, okay? Or if you give the correct decision in context, but you don't link it to the p-value, okay? That's why I always say remember to put the p-value in there. With a p-value of blah, we reject the null hypothesis. That means we have evidence, blah, 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 blah. Okay? Incorrect if you don't do any of that. Let's see. Oh, if you have the wrong p-value for some reason, if you made a mistake somewhere, but your decision is consistent with it, and you give everything in context, then for step 4, which is just the decision and conclusion, you can still get an E. And essentially correct the most points possible, even if your p-value is wrong from the previous step. Okay, so again, even if you do the test wrong, you can still get parts of the question entirely correct. You could make up a p-value for step 3 and get an I for step 3. But if you interpret it correctly and make the right decision, you can get an E for step 4. I think that's pretty cool. Because getting an E on any part of any problem is pretty good. Okay, and based on your responses, E's are worth a point, P's are worth half a point, 4 is the highest you can get. That's if you got all E's, so on and so forth. Okay, so again, hopefully going through these questions pretty closely, both in terms of what the solutions are and how they're graded. Hopefully it makes you feel less nervous about what you need to write on the test. I don't want you to have to worry about that. Okay, if you know how to do the problems, I want you to be confident that you know what you can leave out and what you need to write for your responses. So, keep in mind there is problem set 4 also. That video will probably be right under this one. So if you made it all the way through, good. That's awesome. And take a look at the problem set 4 video as well. Have a great day.